In this lecture, we are going to derive a few finite differences estimates for the first and second derivatives of a function. The estimates that we will illustrate in this lecture are the forward difference, the backward difference, and the central difference estimates. We take x equals a and the corresponding point on the graph of f. Recall that f prime of a is equal to the slope of the tangent line to the graph of f at x equals a. F prime of a is defined to be the limit as h approaches 0 of the fraction f of a plus h minus f of a all over h, provided that this limit exists. This fraction is often called the difference quotient of f at x equals a. Let h be greater than 0. As the name forward difference estimate suggests, we move forward along the x-axis from x equals a to x equals a plus h. We find the corresponding point to x equals a plus h on the graph of f. A forward difference estimate for f prime of a is the slope of the secant line through the points at x equals a and at x equals a plus h on the graph of f. The rise for the secant slope is f of a plus h minus f of a. The run is just h. And so f of a plus h minus f of a all over h is a forward difference estimate for f prime of a. This limit definition of f prime of a also requires that we approach x equals a from the left side. So instead of moving forward along the x-axis, this time we move back from x equals a to x equals a minus h. And a backward difference estimate for f prime of a is the slope of the secant line through the points at x equals a and at x equals a minus h on the graph of f. The rise is now equal to f of a minus f of a minus h, and the run is still equal to h. And so a backward difference estimate for f prime of a is f of a minus h all over h. We can also average out these two estimates and get a third estimate. We take the arithmetic mean of these two estimates so that f of a cancels out, and the arithmetic mean is equal to f of a plus h minus f of a minus h all over 2h. This third estimate for f prime of a is also called a central difference estimate, since x equals a is exactly the center of the interval from x equals a minus h to x equals a plus h. This central difference estimate is also the slope of the secant line through the points at x equals a minus h and x equals a plus h on the graph of f. To gauge how accurate these estimates are in approximating f prime of a, we turn to the Taylor series to find error formulas for these estimates, starting with a forward difference estimate. According to the Taylor series formula, f of x equals f of a plus f prime of a times x minus a, plus the error term or the remainder term f double prime of c divided by 2 times the square of x minus a. The real number c is some value between x and a. And so taking x to be a plus h, f of a plus h equals f of a plus f prime of a times h plus the error term, which is equal to f double prime of c sub 1 divided by 2 times h squared. Here c sub 1 is a value between a and a plus h. Subtracting f of a from both sides, and then dividing by h, we have that the forward difference estimate f of a plus h minus f of a divided by h equals f prime of a plus the error term f double prime of c sub 1 divided by 2 times h. If f double prime is continuous or at least bounded, then the error for the forward difference estimate is of order h. The error for the backward difference estimate is similar. F of a minus h equals f of a plus f prime of a times x minus a, which this time is minus h, plus the error term f double prime of c sub 2 divided by 2 times the square of minus h. C sub 2 is now between a minus h and a. We subtract f of a from both sides. Then divide by minus h. To get the backward difference estimate, f of a minus h divided by h equals f prime of a minus f double prime of c sub 2 divided by 2 times h. Therefore, the error for the backward difference estimate for f prime of a is also of order h. For the central difference estimate, we take the Taylor equation for f of a plus h and subtract the Taylor equation for f of a minus h. F of a cancels out. H minus h is 2h. So we have 2 times f prime of a times h on the right side, along with the difference between the two error terms. We divide everything by 2h. To get the quantity f of a plus h minus f of a minus h divided by 2h on the left side. On the right side, we have f prime of a plus the difference between f double prime of c sub 1 and f double prime of c sub 2 times h over 4. If f triple prime exists, a mean value theorem says that f double prime of c sub 1 minus f double prime of c sub 2 should be equal to f triple prime of c sub 3 times h, where c sub 3 is a value between c sub 2 and c sub 1. Therefore, the right side becomes f prime of a plus f triple prime of c sub 3 times h squared divided by 4, and the error for the central difference estimate is of order h squared. We now derive some estimates for f double prime of a. For a forward difference estimate, we can use the difference quotient for f double prime of a. So f double prime of a is approximately equal to f prime of a plus h minus f prime of a divided by h. We apply the Taylor series formula for f of a plus 2h, and using x equals a plus h as the base x value, so that f of a plus 2h equals f of a plus h plus f prime of a plus h times h plus f double prime of a plus h divided by 2 times h squared plus the error term f triple prime of c sub 6 divided by 6 times h cubed. C sub 6 is a value between a plus h and a plus 2h. Similarly, f of a plus h is equal to f of a plus f prime of a times h plus f double prime of a divided by 2 times h squared plus f triple prime of c sub 7 divided by 6 times h cubed. C sub 7 is some number between a and a plus h. We subtract f of a plus h from f of a plus 2h. On the left side, we put f of a plus 2h minus 2 f of a plus h plus f of a. On the right side are f prime of a plus h times h minus f prime of a times h plus the difference between the order h squared terms plus the difference between the error terms, which are of order h cubed. We divide everything by h squared. If f triple prime exists, a mean value theorem says that f double prime of a plus h minus f double prime of a should be equal to f triple prime of c sub 8 times h, where c sub 8 is some value between a and a plus h. And this is the equation that we get. F prime of a plus h minus f prime of a all over h is a forward difference approximation for f double prime of a. And from earlier calculations, we know that the error for the forward difference estimate for the derivative of a function is of order h. And so combining all the order h terms on the right side, we have f of a plus 2h minus 2 times f of a plus h plus f of a all over h squared is a forward difference approximation for f double prime of a with an error of order h. For a central difference estimate for f double prime of a, we start with the Taylor representation for f of a plus h. After the h squared term is the error term f triple prime of c sub 9 over 6 times h cubed. C sub 9 is some real number between a and a plus h. We will also use the Taylor series for f of a minus h. The error term is f triple prime of c sub 10 divided by 6 times the cube of minus h, or minus f triple prime of c sub 10 divided by 6 times h cubed. C sub 10 is a value between a minus h and a. And so adding the two equations and rearranging the terms, f of a plus h minus 2 times f of a plus f of a minus h equals f double prime of a times h squared plus the error term f triple prime of c sub 9 minus f triple prime of c sub 10 times h cubed divided by 6. If f quadruple prime exists, then a mean value theorem states that f triple prime of c sub 9 minus f triple prime of c sub 10 should be equal to f quadruple prime of c sub 11 times h. C sub 11 is now some value between c sub 10 and c sub 9. We divide everything by h squared. We get f of a plus h minus 2 times f of a plus f of a minus h all over h squared equals f double prime of a plus the error term of order h squared. And we have a central difference estimate for f double prime of a with an error of order h squared.